All right. Um, let's go ahead and get started. We're in here, and it was in Google Classroom as well. A copy of the PDF. I don't know. I didn't read it. All right. Um, so, kind of getting started today. We are beginning chapter 4. Going through. So, again, just remind you of the plans for the next couple of days, um, weeks. All right. My plan is before we leave. So by Friday of next week, we will have taken a. I'll write a test that's going to be similar to the DE test. It won't be the exact questions. It'll just be one that's kind of the same types of questions. I don't know exactly how the Southeastern teacher is going to phrase the questions. I have ideas. You can only ask these questions so many different ways. So I'm going to give us one to give us an idea of what we're looking at. It is going to be on you over Mardi Gras break to look at the material and be prepared to take a test like Tuesday after we come back for DE. I can't hold it off any longer than that, just because if we don't, we'll get too far behind. All right. That'll give us Monday after the break to review and all of that and answer any questions and then go into the DE test. Remember, just like the quiz, the DE tests are going to be one question at a time, forward only. Not my choice, but that's just how they are. So you won't be able to flag the questions or skip questions. It just automatically marks it wrong. All right. So today we are beginning chapter 4. Chapter 4 is all about atoms and elements. Some of this you might have seen before, especially if you had a middle school teacher that did like physical science and all of that. You might have went over some of the things about the periodic table, some of the regions, things like that. Today we're going to be looking at beginning to look at scientists that kind of came together to give us our understanding of what the atom looks like, our atomic models. We're going to look at specifically the stuff that's highlighted in green. You need to know these elements by name and symbol. We're going to go through most of them today. I'm not going to do all of them, but some of them, the symbol is an abbreviation of it. Others, there's not. So it was an older name, things like that, and we've changed the name since. We are also going to be looking at specific groups on the periodic table. Groups are columns. So like column number 1, 2, 17, and 18, we have to know the names for those specific groups. You should know number 18 already. At least we went over that in class before. And then the last thing, if we get to it today, we'll start looking at the location and charge of the subatomic particles and start talking about the difference between a proton, neutron, and electron as we go through today's material. All right. So getting started, if you take out your periodic table reference packet, there'll be one thing that you notice about that periodic table. If you look at that periodic table, you'll notice it has the symbol, it has the atomic number, it has the atomic mass. But what is it? What isn't listed on that table? The names. So it's going to kind of be on you to be able to know the name associated with each of the symbols. And fortunately for us, we don't have to know every single name of them. All right. I think it's about 25 of them that we have to know the names for. And for the most part, they will be elements that you're already familiar with the name, and you just kind of have to associate that symbol with it. All right. So, talking about atoms, and this is kind of relating to Dalton's law, but we're not totally that, not all of it. But remember that so far this semester, we've talked about atoms in terms of they are what composes matter. That's what makes up matter. How those atoms, the specific property of those atoms that make up a certain material, are going to determine the properties of that matter. So, the fact that aluminum has certain characteristics, when you get a lot of aluminum atoms together to make a piece of aluminum, it's going to react a certain way. Same thing with carbon. Carbon likes to arrange itself in different ways. One of the ways that carbon can arrange itself is in a structure where it makes kind of like sheets, and that's the graphite that's in your pencils. And so those sheets can break off, and as you drag it across a piece of paper, it leaves a line. Another way carbon arranges itself is more in a crystalline type structure to make coal and then eventually diamonds after it's under heat and pressure and things. So kind of keep that in mind as well. An element is a substance that cannot be broken down into a simpler substance. So when we talk about an atom or an element of gold, we're talking about if we break it down any further, it ceases to be that. It can no longer be that. And then if you look at the periodic table up here, notice that up to about element 91, 92, they are all written with these filled in letters. And then after uranium, and then also number 61, notice that they're kind of in those outline letters. So there are about 91 elements that are found in nature. All of the ones with solid writing is natural elements. We can find them digging them up in the ground, in the oceans, in the air, things like that. Those that are written as an outline, they are considered to be synthetic. They are man-made. We have made them in a lab somewhere. Case in point, element 97, BK, is berkelium. They made it in a lab at Berkeley University. All right. Francium. Oh, no, that one was discovered. I'm trying to think of another one that's named off where it was located. Californium, 98 CF, probably in another California university, if not Berkeley again. There are man-made elements that we call synthetic. There are 91 natural elements. Everything past 92 on the periodic table is called a transuranium element past uranium. All right. Most of those are synthetic. Most of those are radioactive. So the exact number of naturally occurring elements, it's not really controversial, but it can vary because some of these that we've created, we may just not have found yet in nature. But we're saying that the ones that we know are found in nature are found in nature. The ones that there are some that are kind of iffy if we found them in nature or not. So just know that. And since they are radioactive, the ones that are past 92, sometimes they may have existed in nature, but they've already decomposed into something else. And so they don't have a long enough half-life for us to see them over time. All right. So I'm going to freeze right here. Does everybody have what they need off of this one? I can leave it here for just a minute. All right. I know some of you take notes on the computer, so there's going to be like a shortcut for you to do this if you choose to use it. Otherwise, you're going to have to copy some things down. But if you go into Moodle and open up the outcome sheet, if you're taking notes on the computer, I'm going to go ahead and pull this up. I'll come back to this if we need it. But if you're taking notes on the computer and you want to do this, click on the outcome sheet. When you click on the outcome sheet, it should open up a Word file or a Google Doc. But I want you to go ahead, the highlighted green section, all of the element symbols that are listed there are the ones that we need to know. So I want you to create a page. We're going to go through and name a lot of these, especially the ones that are like oddball names that the name and the symbol don't match up. So, so you can do that. Ultimately, the way that I'm going to write it on here is if we look at the sheet, it's going to look something like that. So let me see if I can zoom in just a little bit. There it is. All right. So once you go ahead, copy these down. If you go into Moodle, you can get the list of them, copy and just drop them into your document. We're going to go ahead and start naming some of these. So I'll give you a moment to get them down, and then we're going to do it. So it's 4. All right, so about 50 elements that we have to know. All right. Yes. Say again. Like what's it called on Moodle? Oh, it's just the outcome sheet. So look at chapter 4. Look at the outcomes, or the it's the one that says learning objectives for chapter 4. That's the file. Let's see if I can. Now, just know that this is not an all-inclusive list. Sometimes there's going to be some on here that Like there'll be some that we come across from the periodic table that we may not identify the name of it right now, but we will. Elements you need to know. Elements that we need to know. These are the ones that are going to be quizzed on, things like that. All right. All right. All right. Oh, there's another one. AL. I is going to have a little line with a dot on it. All right. And then the other I, the one that's just an I, is going to have a line at the top and the bottom, not just a line. All right. So the ones that I have circled, these are all elements that when we first started doing the periodic table, sort of started creating the symbols to go with the names and all of that, they likely had a different name, an older name, usually Latin or Greek, something to that extent, that we no longer call them by the same name. So the symbol and the name don't match up. The majority of the rest of them, the symbol is going to be sort of like an abbreviation of the name, but it's not considered an abbreviation. It's called a symbol. All right. So I'm going to start with NA. Does anybody know the name for the element that matches the symbol Na? Close. Starts with an S. It's common. It's in salt, sodium. All right. All right. Sodium. All right. What about the element that has the symbol K? Starts with a P. Potassium. All right. Potassium. All right. Another common one that you've probably seen the symbol before and you might recognize it, but Fe, what element does that represent? Iron. All right. Now, I do know the original name for iron used to be ferrium, Ferrium, and that's why it's Fe. But now we call it iron, or we call it iron in this country. All right. What about Ag? It's one of the precious metals. A lot of Au is gold. Ag is silver. All right. So the original name for silver was argentium. The reason why Argentina got its name is because there was believed to be silver in the mountains in Argentina, because that's what the natives told uh, the explorers whenever they got there, and so they were trying to go and ravage the land for silver, and they never really found it. There is silver there, just not in the quantities that they originally thought. All right, now we're kind of whittling down the list, and we're getting past ones that are maybe as the more common ones. So, SN used to be called stanttium. Um, does anybody know what we call it today? It's a real common cheap metal. SN is tin. Titanium's not a cheap metal. It's not super common either. Yeah. All right. So SN is tin. SB is a metalloid or a semiconductor or semi-metal. This one is called antimony. ANTIMONY. All right. Now, does everyone know what an incandescent light bulb is? That's the old style of light bulbs that you screw in that have the little wire in it that when you turn it on, it kind of, the wire glows. All right. Does anybody know what that wire filament is made out of? Not copper. It's a high resistance metal. All right. No, that's the new type, or what we use now. All right. So W is tungsten, and that's what that filament is made out of. I need to make sure I spell this one right. All right. So the element with the symbol capital W is tungsten. Um, Tungsten is what is the filament that we used to use in a lot of the old incandescent light bulbs. There were other elements that we used, but that was one of the more common ones. Well, the reason why I circled these is because the name and the symbol does not match. The other ones are going to be more like a abbreviation. All right. And then we get to our last two. So this might give you a hint, but go ahead, look on my board on the wall, look on my periodic table on the wall. Notice that element Hg is written in blue. That means it's a liquid at room temperature. Hg is a metal that is a liquid at room temperature. So what metal is that? Mercury. All right. So mercury is Mercury. And then the last element, yes, last element with a symbol that doesn't really match the name is lead. All right. Now, um, so I'm not going to go through and write all of these other ones. I am looking at possibly Friday. We will have a quizzes type quiz where you have to be able to either, given the name, give me the symbol, or given the symbol, give me a name. All right, it's going to be both ways. All right. I'm not going to, the ones that are maybe a little more difficult on spelling, I'll probably do those as multiple choice. The ones that are a little more common, I need you to spell them. All right. So just be aware that on Friday, we will have some sort of quiz that I'll make available for when you do that. All right. Now, the rest of these, I'm not going to go through and write each one of these down because I just don't have enough room for all of them. But going through there, symbol for element H, what element is that? Hydrogen, He. Helium, Li is lithium, Be is beryllium. B is boron, C is carbon, N is nitrogen, O is oxygen. Those first two rows are probably some of the most common elements that you'll see in this class. All right, you should get to know those pretty well. All right, moving on. Starting on third row with F is the stuff that's in toothpaste. Fluorine, but when it's in an ion form, it's fluoride. Neon is Ne, Mg is magnesium, Al is aluminum, Si is silicon, P is phosphorus, S is sulfur. All right, now while I'm right here, that P and K, a lot of times people see the capital P symbol, they want to call that potassium. Potassium is written with the K, and phosphorus is written with the P. And that's probably one of the more missed combinations on there. Same thing with Mg and Mn. They are two of the more commonly mixed up ones. So going through there, phosphorus, sulfur, Cl is chlorine, Ar is argon, Ca is calcium, Ti is titanium, V is vanadium, Cr is chromium, Mn is manganese. Next row, Co is cobalt, Ni is nickel. And then iron, nickel, and cobalt are known as the iron triad. They are the three most common magnetic metals, or metals that can become magnets. Cu is copper, Zn is zinc, As is arsenic. Zinc, Z-I-N-C. Kind of like how your uncle says zinc. As is arsenic. A-R-S-E-N-I-C. All right. Br is bromine. Kr is krypton. And just so you know, the name Krypton and the Superman comic book name Krypton have nothing to do with each other. They are not even associated with each other. Krypton comes from the Greek root of kryptos, or cryptic, unseen. So it was a gas that we didn't know about for a long time. Rb is rubidium. Sr is strontium. Pd is palladium. Cd is cadmium. I is iodine. Xe is xenon. Cs is cesium. Ba is barium. Pt is platinum. And then Bi is bismuth. Rn is radon. Fr is francium. All right. So, easy way to get these. There are, if you just type in on, like go to Google and you say periodic table of elements, it'll pop up with one that probably has the names and the symbols on it that you can use to study, to check your spellings and all of that. Just make sure that you are kind of keeping up with those and all of that. So I'm going to write this so I don't forget. All right. All right. So the quiz that I do will only come from these that are listed. I will not use other ones in the quiz. The other ones, you'll get familiar with some of them just by nature of spending time with them, but I'm not going to require you to know them to the level of these others. All right. So six. In an effort to make you not have to type so much or write so much, I'm going to do this. 2, 3, 4, 5. Take my pass it back. 7. Take 1, pass it back. All right. All right. This sheet that I just gave you, I'm going to give you about 20 minutes. 20 minutes to go through it. Every answer to every question on there is in the little topic at above. So there's a little blurb about each of these scientists, what they did, and then at the bottom there's a few questions of things that we need to know about them. All right. So you can work with a partner, whatever, but this sheet is going to become your notes. So I'm going to give y'all some time to fill this out first, and then we'll go over it. Using my notes and all of that, and kind of highlight the things that are important. So take some time, read the little passage, answer the questions about them, and then we will come back together in about 20 minutes. So everybody should have had a chance to work on this a little bit. You should have gotten most of this sheet done. So we are going to go through and fill it out and check these answers as we're going through. The idea behind me giving you the sheet to work with rather than just putting it up there is this should save you a little time on the notes. I'm going to go. I'm going to, as I'm going through the notes on this, don't feel like you have to copy everything down on the slide. The stuff that's on this sheet is the important highlights to it. Anything else, I'll make sure I emphasize and all of that. So kind of going into it. Now, I do want you, this is not one of the scientists that was listed in our sheet there, but I do want us to know about Democritus. Democritus lived between 460 and 370 BCE. He was a philosopher. Democritus is the person that was credited with, or the first person we credit with describing the smallest part of matter as atomos or atom. So he's the person we give credit for naming the atom the atom. He had no idea other than just a philosophical journey in his head of imagining what would happen if I cut something down till I can't cut it anymore. And so he gave it the name atom because atom means uncuttable. So at some point he imagined that a piece of matter can no longer be separated anything else. Now, so in his vision of an atom, it was just some sort of solid particle. He didn't know anything about electrons. He didn't know anything about protons. He didn't know anything about charges. He just knew that these atoms are, and in his mind, an atom and a compound were no different. Water, the smallest part of water was an atom of water to him. The smallest part of carbon was an atom of carbon to him. So just be aware of that. So really the only thing that we need to know about Democritus is just this part, that he coined the term atom. That's where we get it from. All right. Now, these statements are already on the sheet that you have. What you'll find is, so Dalton's atomic theory, sometimes it's split into 3 parts, sometimes it's split into 4 parts. On the sheet right here, you have it split into 4 parts. I actually prefer the 4-part split. All right. But in basic, what Dalton taught us, or what Dalton stated about an atom, was that every element is composed of tiny particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from other atoms and elements. So each atom is unique in and of itself. All copper atoms have a certain number of protons in common and a certain structural shape in common. All right. And then his last postulate that sometimes gets split up in a little different way, or actually they split number 2 up, and then I'll make another statement. Atoms of the same element are the same. Atoms of different elements are different. So if you're comparing copper and gold, you should be able to see at the atomic level differences. We know today that those differences have to do with the number of protons. All right. Back then, they weren't sure what made it different, but they had an idea that they were different. All right. And then the last statement is atoms combine in simple whole number ratios to form compounds. So remember, we talked about that these ratios for a compound is fixed. So for like water, it's H2O. For carbon dioxide, 1 carbon, 2 oxygens, things like that. All right. So looking at his sheet, it's not a space bar. Looking at the sheet, just kind of going through here. So what is the name of Dalton's theory? You should have gotten atomic theory. What are all elements made of? Atoms. An atom of hydrogen and an atom of carbon are different. Specifically, hydrogen has 1 proton, carbon has 6. Compounds are made of different elements, different atoms. And then if we were to look at a if we were to look at a molecule of HCl, what is the ratio between hydrogen and chlorine in this compound? Should have been 1 to 1. Now, something that wasn't included in the little packet thing about Dalton, Dalton did describe an atomic model. He called his model the billiard ball. Does anybody know what billiard is? It's pool. It's a different version of pool. It doesn't have numbers. It has colored balls that you hit in different locations and things like that. All right. So Dalton's idea of an atom was a solid sphere. He didn't know about charge. He didn't know about anything. He just kind of said that atoms, in his mind, looked like a solid sphere or a pool ball. All right. So the next scientist that we dealt with is Thomson. Thomson was another English physicist, and Thomson really was operating he was doing his work on the tail end of Dalton's work. They do have some things that they work together on, but Thomson just kind of furthered Dalton's stuff. So I'm actually going to go to the sheet first, and then I'll come back to this slide because I'm going to use the slide as the example. So going through Dalton, what unique part of the atom did Dalton observe or discover? The electron. All right. So Dalton was able to discover, he's credited with discovering the electron. And what was the charge of the electron? Negative. All right. So electrons are negatively charged particles. And so you kind of have to read between the lines on this. But cathode rays are made of negatively charged particles, so cathode rays are made of electrons. All right, it's a stream of high-speed electrons. All right, and so since electrons are negative, and a cathode ray is a negative stream of electrons, why did the electrons move from the negative end of the tube to the positive end? Opposite charges attract. All right. And then essentially, what was Thomson working with when he discovered cathode rays? All right. Now, for you guys, it probably doesn't mean much because for you, TVs don't look like they used to. They're all flat now and things like that. But the previous iterations of TVs and all of that is these gas discharge tubes are essentially what we eventually made into the TV. All right. The reason why the TVs used to be that long, deep thing is because it was a big gas tube. The gas particles were fired at different parts of it, and it scanned across, and it made the image that we see as it hit and lit up in certain areas. So the black and white TVs were really just cathode rays hitting certain part and causing it to flash brighter or not as bright and things like that, depending on the strength of it. So that his kind of research led to a lot of the things. Also led to X-ray, discovering X-rays and all of that. same similar types of tubes, similar types of energy was being used um, to create these things to make those images. Now, going back to one other thing that Thomson did. So Thomson took Dalton's model of the atom, and he had to find a way to describe the electron using that model. So Dalton's model was called the plum pudding model. All right. Plum pudding is a very English dessert, I guess. But basically, what our equivalent would be something like raisin bread or bread pudding, similar to that with raisins in it. So basically, the way that he described the atom, in order to describe the electrons, he said that the solid sphere that Dalton described is the positive region. So that area of pink on this one would represent just the positive part of the atom. And then he said that they have these little things shoved into that positive region that are negatively charged, and that's what he described as the electrons. He didn't really see the electrons as free flowing. He just saw them as something that maybe we could take out and isolate and fire them in a stream. All right. So for Dalton, know the billiard ball model. For Thomson, know the plum pudding model. Know that Thomson discovered the electron. And he described the electron as a negatively charged particle. All right. Another scientist that started his work just on the end of Thomson's work is Rutherford. All right. So let's go. All right. So by the time Rutherford came on, we were starting to know some things about the mass of the atoms, and we were starting to know some other things about it. It says that Rutherford worked with what were called alpha particles. What we need to know that an alpha particle is basically an alpha particle is a helium nucleus. All right. So an alpha particle is made of 2 protons, 2 neutrons. So an alpha particle is a positively charged particle because it doesn't have any electrons around it to balance off the positive charge. And essentially, it's a helium atom with the electrons stripped off the outside. So Rutherford was able to isolate these alpha particles, and then he fired them at a thin sheet of gold foil. I'm going to show you what the experiment setup looked like in just a minute. But using these positively charged particles, he fired them at the sheet, and these particles had 3 options of things to do. It could either pass through the sheet, it could deflect, change directions, or it could bounce back. All right. So the reason why Rutherford's experiment is called gold foil experiment is because he was using a sheet of gold foil. Why gold foil? Because gold foil is only a couple of atoms thick. So he was wanting something that wasn't very, like firing alpha particles at a sheet of paper or something like that. It'd be hard to get any results. But a very, very thin, micro thin thing he could fire them too, and it has the ability to pass through if it hits an open space. All right. So, how did he know that an atom was mostly empty space? Because, or what did y'all come up with? Most particles pass through. All right. Number 4. So for number 4, as the alpha particles hit the gold foil, some passed through. So some went straight. Some of the particles deflected or bent. And then some of the particles repelled. And by repelled, they just turned around and went the other direction. All right. How did he know that the nucleus was positively charged? Because of opposites, like charges repel. So he assumed that the nucleus was positive because all right. So I am going to have us add a couple of things to Rutherford just because Rutherford, this really sums up Rutherford, and it doesn't give us a good enough overall picture of what he did. So the first thing that I want to show you, and you don't have to draw this, but I want you to be familiar with what it looks like. So this was kind of the setup for Rutherford's gold foil experiment. All right. This stuff on the outside, it's a material that when an electrically charged particle hits it, it will glow. All right. So it'll make like a little light thing. The gold foil was set up in the middle here, and then we had this little box here, lead box, with a known radioactive element that ejects positive particles. So on the front of this is a little slide that he can open and close it, and when he opens it, it fires a beam, or it releases a beam of alpha particles. The alpha particles, when they hit the gold foil, a lot of the alpha particles just went straight through. So he was seeing a lot of stuff lighting up here, which he didn't expect. What he expected was that it's going to hit it and bounce back every time, because he was thinking that that the gold foil was this solid sheet that nothing can pass through it. So he was expecting to see a lot of lights back here, but he didn't see that. What he saw was that the majority of them went straight through, and then we had a few of them that went off at these angles, and so he determined that because they passed straight through, that it was mostly empty space, and because it made these angles, that whatever it was hitting was positively charged, causing it to change direction through repulsion. All right. Considering he was doing this in the early 1900s, 1909, that's pretty amazing because, again, if you think about the technology that existed in that time period as compared to now, to be able to recognize these things and all of that was pretty unique. Huh? They're much smarter than I ever will be, so I don't know. The things that, I was interested in biological things and all of that, so the research and experimentation I did was always patterned off of somebody before me. So it's kind of like that combined human knowledge. He was patterning his stuff off of Dalton and Thompson, and he was just trying to take their research a step further. Um, so, um, I mean, they were able to detect charge, so they were playing around. This is also the time electrical stuff is being developed, electricity and all of that. So they were all playing with these things and not really knowing what to use it for yet. Just like right now, the emerging technology is, even though it's been going on for 50 years or so, the emerging technology is how do we use AI? So we're experimenting with different ways, and a lot of people are doing different things with it, and ultimately it's going to lock into one way. Um, Now, so just kind of comparing Thompson's model. So this is Thompson's model. When he originally went into there, this is what he was expecting. He was expecting the alpha particles to come, hit the atom, and bounce right back. All right. Whereas what he actually discovered is that because most of the alpha particles pass straight through without any interaction, that there was nothing stopping those positive particles to pass through. And then because of the deflection, because of the repulsion, he said that the nucleus of an atom is this very, very dense core. All right. So Rutherford's atomic model. I call Rutherford's atomic model the Jimmy Neutron model. Anybody ever watched Jimmy Neutron as a kid or ever seen any episode? Yes, he has a big forehead. Did anybody ever see or it's like the 1950s drawing of an atom. So if you ever looked at those atoms, so they always had this kind of little dense nucleus, and then they had electrons that were kind of flowing around like that. All right. So that's kind of what Rutherford described. He didn't say that electrons were certain distances away. He just said electrons on the outside and protons and neutrons are in the center. So he described the nucleus. All right. Um, all right. But also know he was gold foil. And then one other statement that I want you to make. Rutherford postulated or theorized that the nucleus made up 99.9% of the mass of the atom. All right. The majority of the mass of the atom is in the nucleus. And we still hold on to that today because in our mass calculations for atoms, we consider electrons to be negligible. Like we don't even really measure the mass of the electron compared to the rest of the atom. All right. All right. Last scientist from the sheet is Niels Bohr. So Niels Bohr's model. Why why do you think they called Niels Bohr's model the planetary model? It was arranged like the solar system. All right. Now, if you did any kind of physical science stuff in elementary school, middle school, you probably saw a Bohr model drawn to some degree. All right. So the way Bohr arranged his model is he had a nucleus in the center that contained the protons and the neutrons. And then he arranged something called energy levels or rings. Come on. All right. So Bohr's model kind of looked like a solar system with the protons and neutrons. I know, I'm just reminding you. Yes. So I'm trying to get you to remember that because you're going to need to know it again. All right. So how do electrons in the same atom differ? They differ in the amount of energy that they have. All right. So what we need to know is that on this first level, the electrons have the lowest amount of energy. As we move further and further away from the nucleus, the electrons have to have more and more energy. So this is going to be low energy in the low levels, high energy in the outer levels. So going through, he also said that each level can only hold a certain number of electrons. So the first level could only hold 2, second level could hold 8, third level can hold up to 18, and the fourth level can hold up to 32. So according to Bohr, we can shove 32 electrons in that fourth energy level. All right, doesn't mean that they have to have that many, but it can hold up to that many. And so in terms of energy, in order to move from a lower level to a higher level, we have to absorb energy. In order to fall from a higher level to a lower level, we have to release energy. Now, Bohr's model is still used today as a teaching model. However, we know that an atom doesn't look like what Bohr's model shows. What Bohr's model is great for is showing us that electrons can only exist at certain distances away from the atom, from the nucleus. All right. But what we use today is called an electron cloud model. It is based off of the work of a few scientists, Chadwick, Heisenberg, the Heisenberg uncertainty principle, and then Schrodinger, where Schrodinger's cat was dealing with a it was not originally a psychological experiment. It was a physics theoretical thought experiment of if you put a cat in the box with this radioactive source element and it's in a box that's going to decay, is that cat alive or dead? Basically, it was talking about, can we predict where an electron is at any given moment? That it can be that the electron is right here and not right here at that exact same time. All right, so it was more about uncertainty and things like that than any kind of psychological thing, which psychology, for whatever, it adopted Schrodinger's ideas. All right,